Hi there. Welcome to the last video we're going to do on dealing with the titration. So questions that are going to come up in question 1. This is the fourth one we're looking at. And it's probably the least likely of the 4 we've looked at, but nonetheless, it does come up relatively often and it has been a few years. So I thought I'd go through it. So it's to determine the water of crystallization in washing soda. First of all, let's just start by taking a look at what washing soda is. So washing soda is this substance here. Okay, so it's sodium carbonate. Okay, with water of crystallization. So it's a crystal. And it's a crystal because it has this water of crystallization here. Okay? Without this crystallization, it would be known as anhydrous sodium carbonate. That would be just simply Na2CO3. Okay? So what are we doing then? Well, in this experiment, we're really trying to determine how much water of crystallization there is in the substance, okay? And by doing that, we're essentially trying to find out the value of X, because X tells us the ratio of water to sodium carbonate, okay? The bigger this value, the more water there is associated or included in the compound per mole of sodium carbonate. There are 2 ways to do this. There is a way you could do it by heating, and there's the way that you'll be asked in question 1 about doing it by titration. Now, it's worth considering how we do it by heating because it does kind of help you understand what you're actually doing the titration. So let's just take a quick look at that first. If we were to heat it, what we would do is basically we would weigh our crystals, which means we're weighing our sodium carbonate plus all of the associated water of crystallization. Now, when we heat that, the water will be driven off. Okay, so it'll essentially lose all of its water of crystallization, and basically what will be left will be just anhydrous without water, sodium carbonate. Okay, so this is going to give us our sodium carbonate. So here you can see in this example, we had 20.6 grams of crystals. We heated it, driving off the water to leave us with 7.63 grams of our pure carbonate. Okay, we can find out what mass of water that is then, of course, by subtracting the anhydrous sodium carbonate from the total mass of the crystals initially. And we get 12.97 grams of water. Okay, what we can then do is basically just get the ratio of these two, the molar ratio, and that will give us the value of X. So here we'll divide our 7.63 by 106, the relative molecular mass of sodium carbonate, and we'll divide the water, of course, by 18, its relative molecular mass, and we get 0.072 moles and 0.72 moles, which gives us a ratio of 1:10. We get that by dividing this value into this value, and you'll get the value of 10. And that tells me that the value of X is going to be actually 10. Okay, and that's how you could do it by heating a sample to determine the water of crystallization. It's probably a simpler, faster method, but not as accurate. And it's not what you're going to be asked in the exam, but it does help you understand what you're doing when it comes to the titration. So let's take a look here. Let's take a look at a question now. First of all, before we go on and look at a question, there's some common questions that always come up here. So make sure with any of these, like any of the titration questions, make sure you know how to wash all the glassware. The burettes, the pipettes are going to be washed with deionized water, and then the solution that they're going to contain and so on. Make sure here that you know how you're making up a solution. Okay, so this is always a part of this question, and we've gone through it in the previous videos. Okay, so you're going to be taking your crystals, dissolving them in a beaker, adding water, dissolve it using a stirring rod and so on, and then you're washing everything, making sure all the washings end up in the volumetric flask, and so on. You bring it up with the wash bottle, the dropper, and then invert it 10 to 20 times. So make sure you can describe that method. That's regularly asked. One other question that's often asked is, as you see in this question, we're going to be doing this by titration against our standardized hydrochloric acid. So make sure, it's very often asked, how did we standardize this hydrochloric acid? Well, we would have standardized it actually using the same reaction, but instead of using crystals with the water of crystallization, we could standardize our hydrochloric acid by using anhydrous sodium carbonate. Okay, so that would be the primary standard that you would use to standardize the HCl that's used in this experiment to react with our sodium carbonate crystals. Okay. So yeah, what else? Well, the indicator will come to. There's often questions about that. So make sure you know your usual definitions about a primary standard and so on, standard solution and so on. They can often come up here. Okay, let's take a look at this question. So here we're told that we weighed out 3.46 grams of our crystals in deionized water. This solution was made up to 250 centimeters cubed, and then 25 centimeter portions of this were titrated against standardized 0.12 molar HCl, and we're told that the average titer of HCl was 21.5 centimeters cubed. Okay, so let's take a look at what we're doing then. So we weighed out 3.46 grams of our sodium carbonate crystals. So again, what we're going to be doing is, when we do our titration, it's important to recognize that what's going to be reacting with the HCl is the sodium carbonate, not the water. So even though we're weighing out 3.46 grams of this, we don't know how much of that 3.46 grams is water and how much of it is sodium carbonate, because we do not know the value of X. That's what we're trying to determine. Okay? But when we do our titration against HCl, the HCl is not going to react with the water. It's only going to react with the sodium carbonate. So by reacting with HCl, our HCl, if we can judge how much HCl reacts, that will tell us how much sodium carbonate reacted, and then we can work back, find out how much sodium carbonate was actually in this solution. And since we know the total mass, we'll be able to find the amount of water, and then we'll be able to find the value of X. Okay, that's an overview of the whole thing. We'll go through it in steps here. Okay, so again, make sure you know how to describe making up this solution from the sodium carbonate that's washed out. Okay, so then we took 25 centimeters cubed portions of this solution, and that's transferred to a conical flask. Now, about the indicator. So here, the indicator we're using is methyl orange. If you're asked to justify why you're using methyl orange, it's because you're titrating a strong acid against a weak base, and that's the appropriate indicator for the reasons we went through before. And methyl orange, make sure you know the color changes. It will be yellow to begin with, and will change to red at the end. Okay, here we're told our average titer was 21.5 centimeters cubed, and that was from our HCl. Okay, so we know the details about the HCl. We can work out how many moles of HCl react because we know its concentration and we know the average titer. Okay, so we can get the number of moles of HCl that react by multiplying the volume by the molarity divided by 1,000, and that gives us 0.0258 moles. The equation will be given to you in the question, but you can see that there's a ratio of 2:1. So the number of moles of sodium carbonate that would have reacted with the HCl is going to be half that number of moles. Now, it's important to recognize here that that's the number of moles in the 25 centimeters cubed in the conical flask. Okay, you can see we have the conical flask here. Okay, but we need to know how many moles were in this solution of 250 centimeters cubed. Now, the simplest way to do this is simply to multiply by 10. If I have that many moles in 25 centimeters cubed, then how much will I have in 250 centimeters cubed, 10 times the volume? Well, since it's the same solution with the same concentration, I will have to have 10 times the number of moles in 10 times the volume to give me the same concentration. So I can simply multiply this by 10. Okay, now that's possible here because it's a nice ratio, 25 centimeters cubed, 250 centimeters cubed. Now, of course, you could multiply by 20 if it was a 500 centimeter cube solution. The other way to do it, of course, and you may have done it this way in class, is basically, well, now that I know the number of moles in 25 centimeters cubed, I could find the molarity. Okay, and once I have the molarity of the solution in the conical flask, I know that that's the same molarity in the volumetric flask. Okay, and then I have the molarity, I have 250 centimeters cubed, so I will work out the number of moles in that. Okay, but it's faster just to multiply by 10, recognizing that if we have this many moles in 225 centimeters cubed, then we will need to have 10 times that number of moles in 250 centimeters cubed of the same solution. Okay, so that's explained there. So here's the number of moles we have in the original solution that we made up. Okay, now what we need to find out is the mass of sodium carbonate that's in this. Okay, because we know the total mass that we weighed out originally. So if I can find the mass of the sodium carbonate, I can subtract it from that to get the mass of water. And once I have the mass of water, I can get the moles, and then we'll be able to get the ratio between the two. So I need to find the mass of sodium carbonate in 250 centimeters cubed. I have the moles in 250 centimeters cubed. The formula mass is going to be 106. So I can multiply by that to get the mass of sodium carbonate in the 250 centimeter cubed solution. Okay, it's easy to find the water then. I originally had 3.46 grams of crystals. So I need to subtract my sodium carbonate from that, and this gives me the mass of water. Okay, now I have the mass of water and I have the mass of sodium carbonate. So now it's just a simple process of getting the empirical formula between the two. There are various ways to do the next part to find the value of X, and your teacher may have done it a different way. I think this is the the fastest, easiest way, but there are other ways to do it, which are fine. So if you've done it that way and you're used to doing it that way, then ignore the way I'm approaching it here. Okay, so I have the mass of water, I have the mass of sodium carbonate. I'm going to, now I have, here I already had the moles, so you can see that I'm not converting the mass back to moles. I do have to do that for water though, because I just got the mass of water. So divide by 18 to get the moles of water, and then I have the moles of sodium carbonate. I can divide this into this, and I get a value of 9. Okay, which means the value of X in the formula is going to be 9. What else? That's pretty much it, I guess. Other questions that sometimes come up, I should have mentioned maybe with the indicator, they sometimes might ask here, why do you only use 1 to 2 drops? Don't forget that the indicator itself is a weak acid, so you can't add too much. If you add more than 1 or 2 drops, it'll affect the value of the titration because, of course, then the indicator will start neutralizing some of the base. And I think that's it. Sometimes maybe they might ask about precaution towards the end of the titration. As you reach the end of the titrations, of course, you'll start adding it drop by drop and washing down the sides to make sure that everything is mixing as you get very close to the end point. That's about it. Okay, right. Stay tuned for some of the more. In the next videos, we're going to go on to question 2, some of the organic experiments. So I hope you found that useful. Okay, thanks for watching.